Yeah, thanks for being here today. Today is a lecture which is probably again at the center of the electronics. So we are talking about the MOSFET and what makes a MOSFET so successful. This is something which is, I think, the core. If anything is interested in semiconductor engineering, it's the MOSFET, and it's a complex device, but it's something which has is still keeping us alive in our digital and our RF electronics. And that's what we. But just as a recap, so we looked at multiple things last time. So we looked at heterostructures, which is semiconductor interfaces, and that was useful in a variety of ways. So only this, the joint combination of semiconductors to semiconductors enables what we can do today with all mobile communication. Wouldn't exist, nothing of this would work, and it would be extremely inefficient. It is inefficient as we speak, but we wouldn't be able to do it. Yeah, so there was this idea. For example, we can put one semiconductor on the other, and by bandgap engineering, and that is adjusting here the barriers for the carriers to travel in the device accordingly, so that you can either suppress a leakage current, which is what we see here. So we want to suppress the diffusion-based leakage. If you have something high concentration in one area, you want to mitigate that. And either you can, and in this case, we are P-based, so we look at the valence band, and we have this additional barrier here. And if you say this is unimportant, yes, you may be right, but not having that would reduce the lifetime of your battery of your cell phone by a third, to a third. Yeah, so really cut it down. This is really vital, and it's this kind of engineering which helps us on the device level to get somewhere. Yeah, so the trick was to get this reduction of dimension. Yeah, so that was the idea, that we use materials to engineer current control. Yeah, so in here, this is a FET situation from the left to the right, source to drain. It is easier to, if you have a volume of carriers, if it's in the third dimension limited, then you just cut it like a tube, and not just like a big reservoir where you have to distinguishedly, problematically also cut it down here, where you're not so sure whether you are able to do that. And you could say this is all physics, but the point is, it makes a difference between something which works efficiently and something which is just does something. Yeah? So that's very key. In the MOSFET, we have something else. So I think some of you have seen the MOSFET, but the advanced MOSFET is, of course, still a device which is so nice and so complex that it's also an academic challenge. Yeah. So, and just you see here that, especially on the right, this is not really state of the art anymore, but I like the pictures. So you see we are talking about a couple of layers of individual atoms. So you can see the individual atoms, and they do something for you. Yeah, so what we see here is, first of all, an oxide. This is the silicon. This is an oxide, and then you have, normally you learn there's metal oxide semiconductor. In this case, we have something in between. There's a third layer, the high K dielectric, because one thing we also learned last lectures was that if things simply get too thin, then you simply have a tunneling problem, because a layer of one atom is not necessarily a solid anymore. So that's very important. So we always tend to point out these things on a photographic level. So this still looks like a solid, but from the property, as we learned from this quantum idea, if you are in the range of the wavelength of the quantum, then the quantum laws prevail. Yeah? And these channels we had here, they are important, because here this quantum well has a an extension of a few nanometers also. So it works only because we are so thin. Yeah? And the same we do here now for the MOSFET at the gate. And the first idea is that is something which is extremely important, and it's surprising that not so many people know that. The nature of these silicon dioxide silicon interface, yeah, is quite exceptional. This is why we use silicon most of the time, because when you have a surface of a material, a lot of things can happen. And the natural oxide, this is what caused in the beginning the semiconductor industry to evolve based on silicon. Yes, germanium is similar, but silicon is critical. And the idea is that we have this in mind, that we can move the band structure at the dielectric semiconductor level. We have that in mind. The problem is that for most of the materials we are getting, this is not the case. So we cannot, if this is the oxide, and here there's the band structure with valence band and conduction band. The problem is simply that you, first of all, have to be able to move them up and down, which is a critical quality that really, and this is the idea of a MOSFET at the end of the day, that a metal, as we say here, so here you can see that the metal is biased, so you put a field there. You learned about the field effect. I think that's something you know already. But what people don't tell you typically is that at the interface of dielectric and oxide, all kind of things can happen. For example, one thing, what is very typical, what happens when you have a semiconductor device, what happens at the surfaces typically? Why is the surface at all a problem? What is changing there? Or when we are having such an ideal crystal, so to say, why is the surface as such a problem? What is changing there? What is the first thing that could happen if you just have an open surface and you just leave it to air or any moisture or so? What would you normally expect to happen? Yeah, some kind of chemical reaction, for example, oxidation. There's a lot of things, nitridation, fluorization. So it's a very good idea, yeah, because these gases are very aggressive. Yeah? That's one thing. But even if you keep that on vacuum, if you just interrupt the crystal, we have a lot of charge potentially there. And what we don't know is whether these charges are really free floating, or whether we have, because of the interruption of the crystal, we create some kind of trap. Trapping is a very critical story, because it's like a situation where you replace something in the crystal by something else, which is doping, for example. And there can be all kinds of traps, and the problem is this is very likely to occur. That's what I'm after. So what I'm trying to pinpoint here is that the semiconductor, the silicon dioxide, is so specific because it is very good. So when you just oxidize it, so that's what people did in the beginning. They just took the natural oxide and it even somehow works. Yeah? And now we have to define working. And what I would like to point now is there are theoretically three, or better four situations. The trick is that the oxide, or the MOSFET, as you know, works on a very specific principle, which is kind of crazy. Yeah? So, and in order to understand what we are doing there, let's first talk a little bit about what should happen if everything is ideal. Yeah? So let's assume we are having an oxide, and it's a perfect crystal, and no interface charges, no trapping, nothing. And the idea, what you typically assume, is that the metal on top of the oxide is at 0 volts, and there's nothing on the interface. So we look now here through this structure, and we just look from the semiconductor to the side of the other. So this is the oxide, this is energy scale, and this is the coordinate which works into this. Yeah. So in the ideal case, which we assume, that both conduction band and valence band, here this is conduction, this is valence band, they just go straight. And what I'm trying to tell you is that this is a very perfect exception. So in any real surface, they wouldn't go straight. Something would happen. They would bend up or down because of charges or because of something which happens at the interface, because there might be charge here at the interface or some defect which avoids it. So assuming a very perfect situation is good. Yeah? So this is something we have in mind. And then what we want is that we can either with a capacitor which we are effectively building, we are either attracting or pushing away holes or electrons. Yeah? So this is the idea. Capacitor, what you learn in school normally, there's a field effect which allows you to deplete or to accumulate carriers near this interface. Yeah? So that would, in the case of accumulation, you would accumulate the holes here. So that's something, because in this case we go for p-type doping in the silicon. That has two reasons, because natural silicon would tend to be p-type, and by its nature, and also we have a reason for that based on the MOSFET ladder. So we could discuss this with electrons, but that is a more difficult case. So let's assume for the moment we have a p background doping, which accumulates the holes now by bending it up. So the valence band also bends up if we just take a negative voltage there, so the holes are attracted. That is kind of reasonable. Yeah? That's something which is not really difficult to be understood. What we tend to do then is that we're defining a Fermi level, which is again the occupied band, which you have then, and this is at some level then, and we relate then the bending of the both bands relatively to this Fermi level, and then all kinds of things can happen. So, for example, if the Fermi level cuts the valence band in this case, then we have carriers really at the interface, but not fixed carriers, but attracted carriers, so to say. So that is one way. The more interesting case, however, is for the fact that we are discussing the depletion or the pushing away of carriers. And what happens then is simply you take a positive voltage and you just deplete this region under the oxide, which again is a very positive situation, because it means that you can really bend the bands down. Yeah? What can typically happen is that if there's a bad interface, what can happen is that, for example, a fixed charge which resides at this interface, because it's bad, of a bad quality, that simply this bending will not work. We call that then Fermi level pinning, so that all the bands are pinned just at the interface, and no matter whether you put a voltage or whether you put a change at the metal, the field effect really doesn't work. Yeah, so you cannot really bend them down. So this is the exception you have to thank for. And so that's on a clean surface you can actually bend it down. Yeah? And what would you get then? That is something which we now have to think a little bit about. So first of all, we would deplete the holes. That's not something which completely kills us. But that is all not related to the MOSFET. The MOSFET takes a very strange idea, which is that you actually want to generate carriers. And the question is, why on earth would there be a carrier generation? Or how would you, when we're in a p-type substrate, why should there be any useful carriers that we can use for something? And then we have to remember something which we kind of touched or not really talked about in one of the last lectures. That was that the intrinsic concentration in any semiconductor is a product. So there is a rule which I'm just going to note down again for everyone. That is, it's good to write it up, that the intrinsic concentration of n times p is proportional to the intrinsic concentration in this carrier. That was a law. We used it just to derive what would be a natural concentration. And that is interesting because this intrinsic concentration is a constant, yeah, for a given temperature. You could say, maybe this is just a law, but that has an interesting consequence, which is quite simple. That is, if you reduce the P concentration near the interface, what will happen to the N concentration then? And this is really a crazy thing, which we kind of have to accept first. When I first heard this, I thought they are crazy. But it's something that you push one carrier away and you get, just out of the nothing, you get 3 carriers and of the opposite type. And this is just a law which directly derives from the distribution laws from essentially, if you ask why is this is the basic law of when you make assumptions about what happens in a crystal, and you learn that specifically this intrinsic concentration is a constant, and this is related then to the N and P doping, or the 3 carriers which you have available. So that means by pushing the P-type carriers away, we are generating some others. And that is good, because if you do that strongly, and this is exactly what we do in a MOSFET, we suddenly create, here we're just pushing away carriers, but we suddenly create near the interface carriers in a positive way. So we have electrons in a P substrate. So this goes up. And this is quite exceptional. So it works for silicon and for some of the very specific high K dielectrics. So this is just something which today we are using. Specifically not silicon dioxide anymore. We use these high K. They have the same properties like these the silicon dioxide, but they form a stronger barrier, because if you just had the silicon itself as a barrier, the problem is the things simply get too leaky. That's why people were a bit worried, and they started to exchange that, because the barrier you build towards the metal on top, yeah, to maintain this situation is just enhanced by the additional barrier that you create by a high K dielectric. Yeah, so that's an idea. So you want to essentially maintain the situation, although it's not just a normal oxide, it may be hafnium oxide or something else. It's just an improvement of this situation. So having said that, the question is now, why is it a gain, and how? So what do you do in this case? By depleting the P, you invert the semiconductor, because you make it N-type near the interface. Yeah? And that is an automatic story, which is very similar to what we did with the heterostructures. Yeah? Because now you're gaining electrons, conductible electrons near the interface, and that's again this tube idea. So you have a surface, and you keep the carriers very near the interface. That's cool, because we again create a pipe, which we then can cut. Yeah. And there was this control idea, and this is very specific. What is the idea of a switch? The idea of a switch or of some transistor is, with a relatively weak input signal, to have a strong change of the current. Yeah? And the first idea I want to plant in your head is that control has to do something with proximity. So I cannot control somebody sitting up there, but if I have somebody very close to this interface here, I could potentially have better control there. You could say this is a very human argument, you're right, but the point I'm trying to make is the switching of the current. So, for example, you could call it, how strong does the output current change over input voltage? This is directly proportional to this proximity. So we want that. We want to keep it near. Yeah? That's very important. You want to keep things very near the interface. Yeah? Now let's talk a little bit about the nature of this. So when we are talking about other semiconductors, what happens then? The question is, would we find other semiconductors which would be even better than silicon? And the answer is there's very few where this works at all. Yeah? So many semiconductors, the Fermi level at the surface is not flexible. So you cannot really move it up and down, but it's fixed somewhere. And this typically leads to a situation that you just deplete the surface. So no matter what you do with the voltage on top, you don't get it nicely turning up, bending up and down. Yeah, that's really a problem. And the question is now, what do we add now? So we have, on the one side, we have now the gate. We just talked about an oxide, metal, semiconductor contact. And the other thing is just to review a little bit the PN junction, which we also have available. So there's a diode. And just if it's very abrupt, we have some situations. So in this case, it's another structure, which is again p-doped silicon, and we put n-doped silicon in the vicinity. And why is this now important? The importance of this is that, first of all, what happens? The PN junction is a relatively complex matter also, but let's first review what is happening. The first thing again is that the Fermi levels in both semiconductors meet. There's no voltage, and there will be a bending up of the valence band and the conductor. So in the case of the p-type, the conduction band goes up, and then we have in the n-type silicon it goes down, and then we can now vary the difference. So there's a depletion layer formed between them because in both, so what happens when they touch, there's a diffusion of the carriers inside the region, they recombine, and there's essentially a region where there's no free carriers available, which is a good situation. So that's why it forms a diode, and you can favor, first of all, this extension of this zone, so you can make it smaller or bigger just by bias, which you apply to both sides of the semiconductor. And again, this idea, why do we need this additional component? That has to do with the idea that let's form it this way, that when we want to control something, the idea of a switch in a MOSFET, or also the amplification ideas, is always to make sure that something is turning on and off. Yeah? So favoring current flow is one thing, but the other criterion for a good switch or for a good amplifier is that you also are able to turn things down. And the PN junction is particularly useful in a sense of isolation. And that's what I want to explain now. So if you have such a structure, what do you want? So you want, in a very near and low dimensional variant, you want to control current. So that means you want to have the current flow here, but you don't want it necessarily down here. And again, why is that? Because turning a switch on is one thing, but you definitely want it off. So we're always discussing how is that ratio. The digital people talk about the on-off ratio, so just how much current is flowing when it's on and how much leakage is there when it's off. Yeah? And when you try to put that into a localization, you want to have, if you only have a current flow in a specific region of the device, then you are very sure that you can switch it off and on if you influence this region. What should not happen is that there are parasitic currents maybe flowing down here, or I mentioned already gate currents. This is something which we also have to add. Yeah? This is a very important thing. Yeah? And this started with a very large extension, so that in the beginning it was this famous long channel MOSFET, which nobody used since 50 years, but everybody still talks about it. Down to 2013, that's 22 nanometers, and we are down to 3 nanometers today in the latest iPhones. That's a bit. I've stopped talking about this because at 22 nanometers we are going away for the same reasons from a 2D device to a fully 3D device, because there's the quantum hitting, as we discussed last time. So there's a specific need also below 20 nanometers to consider also the quantum effects. But it's important to understand the MOSFET first and then the quantum effects, and not vice versa. And the point I'm trying to make is now this combination of effects. Yeah, so this generic oxide, or the oxide on top, makes sure that there is carrier formation along this interface. Yeah? And the trick is now that by the application of 2PN diodes, you again create a situation like in the bipolar, that you everywhere else, you are getting a situation where you have two anti-parallel diodes. And two anti-parallel diodes, apart from some leakage, is just not conducting any current under any circumstances. So we have created essentially an ideal, or maybe even a real off situation. So when we are now trying to send a current from here to here, the first thing you organize is that this thing is off. And why is this off? Because you're making a doping profile here, and the stronger you pronounce the difference here, the stronger also the diode isolates in this sense, unless you put it to a forward situation. Yeah? And that is what helps. By the way, why do we dope the N regions very high? What is this thought? I think we had it last time. Why do we put so much high doping under the metal contacts at the source and at the drain? What is this idea? Any thoughts on this? So why do we also like doping the drain and the source region highly? Remember it's very simple. So remember what we want to do. So we have a metal, and what do you want at the interface metal to a semiconductor? What should be very good there? Well, what happens if we don't dope? What type of contact do we get when we are having metal on top of the silicon without doping? Do you remember that?
Schottky.
It's a Schottky diode, so it's not a good one, but typically it would be a Schottky diode. And then we were trying to, again, this was this idea of this tunneling, that we put so many carriers near the interface that this Schottky contact then transforms by increasing the density of states at the interface, you would say physically, but it's very simple. You just put as many carriers that they tunnel through this Schottky diode created, and then you effectively get a very low resistant ohmic contact. Yeah? So it's about the resistance of this region, but it's also definitely of the contact region, which then is suppressing any inhibiting effects. Yeah? So here we are good, and here we are particularly isolating. Yeah? So we are not sending any carriers into the substrate, which would be bad, because if we're trying to control here and something would be flowing below the p-type silicon, in this p-type silicon we would have a significant problem. Yeah? Now, what do? We combine these two effects now. And why does it open now? And that's the point, and this is why this oxide contact is so useful, that we now, by creating an inversion layer, we send here electrons into the p-type by inversion, by just doing the right voltage. And the nature of this is important. This is, of course, you want to use the field effect, but the field effect is only your control. Yeah. And you can now add the field effect because you have a depinned surface. This is the critical story. So you are able to create that inversion because you have a depinned surface, and secondly, you are now able to move them up and down. So you can interrupt the flow of electrons at a specific point at this interface. That is the key story. Yeah? And what can happen now? We have two situations which are useful. So there's the first one is there's an unsaturated case where we are just allowing this to happen. So when we are not really there's now, because we now have three contacts, we have a kind of a distinction to make. Because if we apply voltage relative to the source, we have to declare what we do at the drain. That is important. And there's two situations now. You can essentially, if you pull hard on the source to drain voltage, then there will be a depletion here. And that is quite easily understood because the inversion is created, but the carriers are sucked out. And there's only, if there's a replenishment, so to say, this is one way of expressing it, then you, by the order of the gate voltage, you could activate that again. So you are reflooding something which is generically off. So we have this generic, we are here, and we are flooding this channel from the side. So we can very nicely control that. There's another situation, if we're not pulling strongly, there will be no sucking out of these electrons to the drain. And then we control very intensely the concentration, like in the 1D situation with the MOS cap. And that's important because in this case, this is something which is just kind of a regulated resistance, as you could say. So you're just controlling the resistance in this thing, but there's not really necessarily an interruption here. And this interruption is critical later on when we are starting to either expressing it in terms of amplification or in terms of on-off ratio. That's similar. What we haven't declared is that all these voltages have to be seen to a certain threshold. So this threshold is introduced because the definition of when this is happening at a positive or like a negative voltage, this is not so clear. This is strongly structure dependent. So the effect will always take place, but the question is, does it necessarily do it around 0 volts, or is it because of some charges somewhere -1 volt or +1 volt? That is still under debate. So that's why we are introducing the secondary threshold. And this is just an explanation, and what we have to do now is to think what would happen ideally if there were no other charges. So essentially you say there's no current, and if we do the right effect, then we positively deplete at the gate, we deplete the carriers, and the more we deplete, the more carriers we create. The more we deplete the holes, the more the carriers we create on the end side. So that's why there's channel forming. So we induce this channel, we don't dope it. That also has some fundamental advantages. Okay, so we have the two situations, and now what is typically used, but what is not correct, typically is just that you get a charge under this in relation to the MOSFET, and this is the famous long channel equations that you say there's a width, first of all, of the gate, which is just in the third dimension, which we don't talk about. There's the length of the gate, which is this length, the channel length essentially. There's an oxide capacitance, and then there's this difference between the threshold and the gate voltage. The surprising thing is that these equations work pretty well. They don't give even nonsense, even in the quantum domain. So they have been introduced for long structures, for 10 microns or so, very low frequency, but they work particularly well when you calculate up to very small numbers, even if you have very thin oxides and so on. So that's just to explain that a little bit. Now we have to turn this idea into RF. So I just talked about digital, and we have to understand a bit what we do with these situations now. So we have this inversion created, and the question is now, what is now the difference between a controlled resistance and something which amplifies? Yeah? And that is something which we just can understand very easily when we go back to something very fundamental, yeah? Which is that when you look at this from an electrical perspective, there's two things which you want to do when you want to amplify, and the same is true when you want to switch. That is that you say, first of all, what do you want to do the current with the input voltage? What is this? So when you change the current, what property do you want from the output current to react to the input voltage? How would you formulate that? So you have a switch, and now you're switching, and what do you want the output current which you're switching do with the input voltage, and why? So you want to go forward, you want to control current, so should it be strong or should it be weak, or what would be arguments for or against each of those? So why would you? So how should the output current, if you think of an amplifier, react to an input voltage? It's actually quite simple. Huh? Yeah, and not just increase, of course, but relatively. So should it be strong or should it be a weak link? Yeah, should be strong, of course. And why? Because, for example, if you think in terms of digital things, yeah, you just want to represent a bit. So with a minor effect, you want to cause the bit to flip, which is essentially what we all have in mind when we do any digital. Yeah? However, I want to make a very clear distinction between the two situations which we have on screen here. The point is, in one point you have a situation like that, and in the other you have a situation like that. If you're just controlling without pulling here, if you just control the resistance, you just change by a voltage relatively a carrier concentration. And this alone is not giving what we want from the switch. A good switch has exactly what you said, has a strong change of the current. It's not just that you turn it on and maybe it comes at some point. You need, in a fast switch, you need this amplifying component, which is an analog argument, but you need that. And we have to understand why that is the case. And there's a very good argument if you just express the maximum gain of something. It is not only related to what you do from the output to the from the input to the output. So this is the transconductance here. So this is this element driving a current here from source to drain based on an input voltage. This is obviously helpful because we have a forward gain. Yeah? But the key thing is that the output is very critical, because what you don't want in anything which is amplifying is that the voltage is also modified. So the voltage has to be steady in this case, yeah. Because if you control a water flow and there's nobody pulling anymore, then that is not really effective. Yeah? You have to get this component in, and power is the product of voltage and current, and the change of the current flow is only useful if the voltage is constant. Yeah? And this is expressed by an additional output resistance. Yeah? So the change is only useful if this output resistance is particularly high. If the output resistance would be low, then the gain goes down. That's because you don't really change something positively. Yeah? And that's just the idea of gain. So you just only, there will only be an effect in the sense of amplifying power in this case if there's a steady resistance you are working around. Yeah, that's a key thing, and this is expressed here that there should be no current change based on the output voltage change. This output voltage change should be independent. Yeah? And the input should not be modified. These are the two constituents of amplification. That is very key. People tend to forget this only because otherwise it would just be resistive. You just change the current, but in the same way that you change the current, also the voltage varies, and that doesn't have a continuous amplification idea. Yeah? So that is one thing how we look at that. Yeah? And the second thing is that you can also look at this from the idea of dynamics, which we haven't talked about yet. And putting a strong current change, there's also a drawback, because what is the problem when we have, I told you that controlling a water flow is good if we keep it close. Yeah? But if you look at this capacitance here, if you make a capacitance and the two electrodes are just getting very close, what happens with the capacitance? So I sold you something and I told you, keep them close, then everything is good. But if I get the carriers closer to my gate, what will happen with the capacitance relatively? So if you make a capacitor and just put the two plates together, what happens with the capacitance? I think it's even standing there. I just saw it when I came in. It fits perfectly. So I'm not really believable because I just told you something which is apparently nonsense. So I said I want a strong change, but I'm also increasing the capacitance. Yeah? So somehow this forward amplification is good, and I'm sticking to that. The forward amplification is good. But fundamentally understand why people have, apart from making the devices so small for area reasons, why people have done this scaling. Why do people cut this capacitance? Yeah? So the control aspect, this is the forward current component which you need, but this capacitance kills you if you're not serious. But then you have an answer because Gordon Moore said, let's make these transistors small, and the idea was, okay, let's make this small. So we keep the carriers close, but we also reduce the length of the channel. And by that, you have a very viable way of reducing the capacitance, despite of the fact that you're making the capacitance very controllable. Yeah? So this is it's a bit contradictory, but you have one effect which is very clear. So control the carriers, but in the current component, the current goes up extremely strong. But at the same time, we have to get this capacitance down. Yeah? And that is why we are reducing the length, the gate length, which is the channel length, significantly. And this can be expressed when you, for example, now check a quantity which is a simple definition of the cutoff frequency of the current gain. Yeah? So obviously it's good if this transconductance, the forward, if this is high, then you get a forward component into the story, which helps you to get the current gain cutoff up. If the capacitances are high, then we are in trouble because then this will delay us. Yeah? And if you want a simple explanation for this FT, if anybody has done some analog, I'd say a digital ring oscillator, so the frequency at which the device would be oscillating itself, if just left alone. You can build a simple ring oscillator, just feeding the output to the input, and see at which frequency this happens. And this gives you a time constant for such a FET. And in the first order, this this time constant which you then get is the inverse of this cutoff frequency. So it relates very much to something you might have seen before. Yeah? So it's just what the digital circuit of the same transistor would do. Yeah? What I want to get across is that the analysis of such a FET is very helpful in two ways. So we have a forward component based on the current, but we also need this very good GDS, so no voltage change, and this explains, coming back to the MOSFET, why we are so particularly interested in this situation. Yeah? So in both cases, the gate controls the current flow, but we want to achieve a situation where if this VDS is high, we want this channel resistance to be there, that we just have a good control of the current flow, but at the same time maintaining the voltage and not, as here the voltage is proportional essentially to the current, which is not an amplifying element. So at the given voltage, that's why we need the saturated region of the FET, and I hope this becomes clear. And here it's a bit expressed a bit stronger. So this is, again, this cutoff frequency. So this is just the idea of RF, up to which frequency something will be working. Yeah? And it's just like, again, the stronger I change the forward current, the better. And then I have two capacitances and the CGS. This is the gate source capacitance. This is essentially this capacitance. Yeah? There's also a second component because we are directly including that. So in first order, you could even cut that feedback capacitance out. But typically we include that because it's always a 10% effect in the whole story. So it's always wise to include it. Yeah? So it's also charged and discharged. So that's why it's directly in. And there are some numbers now. So this is something which we would like to look at. So this is now the understanding in very principal terms from the MOSFET. The question is now, what else matters? Yeah, and you see here, just maybe this is for such a device, you get numbers, and the point is that these numbers which we are getting, which we just extracted from a DC and maybe a little bit of AC analysis, they work wonderfully also out of these S parameters we talked about. Yeah? So in this case, we are not really measuring currents. The only thing we are doing, we are extracting, based on these high frequency parameters, which we have here, the representation of these FETs. Yeah? And you see here, there's suddenly a lot of additional elements appearing, which we need to consider. Yeah? So for example, we just already talked about the GM and the GDS. This is this idea that we change current over high resistance. And the other thing is that there's, of course, also, apart from the input capacitance, there's also an output capacitance, which is understandable, I would say, because when you look at such a structure from source to drain, then it's clear that something will couple here between the two. And it's a dynamic equivalent of this resistance which we have at the output. Yeah, so that is, I think, okay. Why we are discussing a little bit further is that at the frequencies where we are at, there's also a lot of parasitic influence. And you see the real cutoff will be lower than what you just would generically get from the intrinsic device, because you have all kinds of corrections. For example, what I just talked about, there's a proportional reduction by the contact resistances at source and drain. If they are high, you lose speed, very clearly. And there's also a direct impact even in this. It's a different approximation, which is a bit better than the top one. You just say we have also a direct influence on the speed in terms of GDS. So it's not just the capacitance, but there's also a direct influence. So you can understand that. And here you see some values just to give you a flavor of what you are getting for a microwave FET. So the CGS is in the picofarad regime, so 10 to the minus 12. And a modern MOSFET would have 10 to the minus 15. So in a modern MOSFET, we would talk about femtofarad. And here you see also that the ratio of the, as I said, the input and the feedback capacitance is significant. So this is way higher. So we are trying to suppress the feedback capacitance for other reasons that will come. Yeah. The output capacitance is relatively low, and the forward here it's directly compared. The forward amplification in relation to this current change, which we both express now in terms of not resistance, transconductance over resistance, but we say transconductance over output conductance. And you see that just the ratio is 375 over 15, so you can even divide that. What is it? It's a factor of 25. Yeah, so there you can really directly see this maximum gain, which can be achieved, because here you can get the direct reading. It's 375 by 15. So if you get this down, the slope, and the current change up, you win amplification. Yes, it's a very simple but useful argument. Yeah? And also why I was talking about the other things, for example, you see there's also, these values are always given to the third dimension. So this is why always there's this millimeter appearing, because it's clear that a larger FET, which has the same gate length, channel length, has a different capacitance than a smaller one. In order to take that out, we always relate most of the things just to this length. It's the third dimension, which we are not seeing. So this is essentially, when we are cross-checking, not to confuse you, here this is a 2D cut, and we don't know in the third dimension how long it is, and in order to say that, we always give the values relative to 1 millimeter of length, which is not always technically useful, but you have the same reference, so to say. Yeah, so that's. And you see there's also significant inductance involved. Yeah, so picohenries, that's just values we have to deal with. Yeah, that's what a line does. And also the pad capacitances here, you see these are femtohenry, just to give you a flavor that a piece of metal, when you put it on the substrate, you get even additional contributions. And then, how did people come to that? You measure them here from 0 to 50 gigahertz, and you see then that with accounting for all that, you get a relatively good agreement between the idea you have of this FET, the model, and what the FET actually does, what it does in reality. Good. So how would you make a FET fast? What would be your answer? Or what has made the FETs fast in the last 50 years? So apparently they became fast. It's just to review, shortly to review what was beneficial when people were doing all the scaling. Why did the what are measures when we went from 10 micron to 65 nanometer gates or 22 nanometer gates? What was significantly reduced? Yeah, and now if you speak of these terms here, what was specifically reduced here? The gaps, both gaps, yeah. So that's the first thing. So because of the shrinking, you get a very much lower value for C in absolute, but also versus the third dimension. And the GM, why do I insist so much on this? So you could say just reducing the length of the channel would not influence the GM. Why does the GM also go up? Which argument drives you towards that? What do we all also do? So, yeah, that's good. That's a smart answer. But there's something even before that. Yeah. So, in which way do we get the? So, which measure has really when you look at this construction here, which measure has really cut the also or increased the GM? When you just think from a long channel MOSFET with 10 microns. So what has also gotten very small in this example here, when we are going back to this? What in this has made GM high? Think of this idea of control or current control. Just want you to phrase it. What would happen if we just cut the length of the channel? It would give us less capacitance, but what could go wrong? The GM could, for example, be steady. Yeah? And what did people, I think you have heard the same arguments earlier in some other lectures from the digital argument. But what has happened with the oxide thickness over the last 50 years? Reduced, exactly. And this is the scaling. So if you make something smaller in this direction, you also have to make it smaller in this direction. Yeah? And the digital people would mainly talk about the on-off ratio. Yeah, so keep that in good shape, because when you don't do that, you lose. If you keep the oxide thickness large, then you cannot really turn the transistor off nicely. It's a direct consequence, because you cannot get a sharp control towards off. Yeah? And in amplification, what you're saying with this is that you have a strong change of the output current to the input voltage. It's the very same argument. Yeah? And this is why people have worked on this so tremendously. So in this sense, we are getting a very nice value. We're getting a very nice transistor. And just to distinguish it a bit, this is what I would like to do now, is just to explain it a bit in the numbers. Yeah? So what you see here is why something is actually amplifying. This is just the current part of it. You don't talk so much about capacitances in this diagram, but it's just important that we get a feel for why things are happening. So I told you, and this is what you clearly see here, is if this transfer characteristic, output current over input voltage, is steep, yeah, we learned that it will give the maximum gain, but you need to see it. Yeah? And what you see is, if this is a strong function, that if you operate at a given voltage the output, and you have a strong change of the current in this direction, then this will be very beneficial for your power change. Yeah, so you can suddenly see that you're modeling power and modulating power. And here you also for the first time see this GDS argument. If the GDS, so in this region, the current is essentially changing with the voltage. So that's very steep. Yeah? So when you increase the current, you also increase the voltage. In this region, the voltage is steady, and the more steady and relatively the more flat this is, the better. Yeah? And so this is just a justification of this formula here, that it's not just about this forward current change, but it's also about this being low. Yeah? Because if you plotted gain or speed of these devices in this regime, in this linear regime, the FET might have a little bit of gain, but typically it would be not strong. And the real strong gains you get in this region where there is a flat output. You need both. Yeah? And the transconductance, just to say that this GM, you could directly plot this if you just derive this equation here. So if you just take this curve and make the derivative of it, it gives you such a peaky curve. So like depending a bit how the slope evolves. Yeah, then you see suddenly, yeah, that makes sense up to a limit. Yeah, so it's very clear we also have an upper limit here, and this is also certainly working against us because having thin layers means that the voltage capability is typically reduced. So the smaller we get, in general, we lose voltage. Because some of these things also, when you excessively bias them, they break. So that's something which limits us here. So that's where you start to understand, okay, there is a limitation, but for a given voltage, we are now changing a current at a given voltage. And of course, if it's higher, that's one thing, it's better, but if it's, yeah. And then the other thing is, which also helps, is that when what is the channel resistance when it's on? This is basically defined again by the switch here, because we want to send the current from here through this box to here. So if any resistance is in the approaches, that will add to the losses. Yeah? And you see that there's also a lower side for the current to swing to, or the voltage. And that is essentially defined in this region, in this linear region, where we have inversion, but it's more resistance which we control here. So in this region, and RF-wise, this is also interesting. It's not for amplification, but we can control a voltage, so you have a controllable resistor with little or no amplification. That can also be a nice function, but it's a different one. It's not for amplification as such. Yeah, this is just the same thing. And also in the numbers, it's both the voltage and also the current in relation. So you remember I talked about this plot of mobility over band gap. Yeah? And here you directly see now the electrical consequence. If you have a high mobility, this max current will be high. And if you have a high band gap, you have a large voltage capability. Yeah? And that translates then into a decent relation between current and voltages. Yeah? And the big problem of CMOS today, of the MOSFETs, is, I think you said that already, is that this voltage is apparently not 20 or 30 volts as it used to be, but we are down especially for the fast devices, we are down to 1 volt. Yeah? And this whole, so that you get a very decent current change, but not necessarily a good voltage thing. That's the limit. Yeah. And that's why in this curve, mobility versus band gap, we always want to the top right in order to increase the combination of the two. Yeah? That is the key challenge. And one thing I want to show you is that you can really see this now. Yeah? So this wave idea can really be shown. And here you see really now the combination of speed and power at high voltages. Yeah? And this is a diagram which is not so easy, but it's understandable. So the first thing we look at is we have an input power which is given at a scale, and this is given in dBm. This is relative to 0 to 1 milliwatt. So we give a logarithmic scale there, and the advantage is that if it's linear, we get a flat characteristic. So you can see, for example, just to explain what we are seeing here, you have an input power of 18 dBm plus 11 dB of gain at the same point gives you 29 dBm of output power. So very simple. Engineers are sometimes lazy, and that's good because you want to see things nicely. So there's a flat gain here, it's the same, 22, 24 plus round about 11 gives you 35 dBm of output power. Very simple. And then the only thing you have to know is that 35 dBm is roughly 3 watts, so 30 dBm is 1 watt, and 36 is 4 watts, and you get a feeling. So that's what else can we see here? That this is a high frequency. This is 10 gigahertz. So we got gain. So we have amplification, 10 dB, 11 dB of gain. So this is obviously working. And you can also see that with the change of the supply voltage, so how much voltage can be put here on the high end, yeah? So we are changing this supply. So in one case it's 25 volts, in another case it's 30 volt, and then 35 volts. And then we change the swing here. Current is constant, so power goes up. Do we observe that? And the answer is yes. You see the blue curve is taken at 25 volts, and then if you're reaching a limit, then the FET already starts to compress. But we can apply more voltage. That's the green curve, and then the red curve. And you see that at 35 volts, the device is compressing at a higher level. So you see that this device essentially is delivering 5 watts of power. And if you bias it at a lower voltage, it's only doing something like 2.5 watts of power. And what you also see is that is the definition of the efficiency, that the efficiency overall is quite lousy. At high frequency, you get, in this case, something like 30% of conversion. 70% is turned into heat. Yeah? So just to give you, so this is not a MOSFET, but just gives you a flavor how this can be looked at. And now comes something which you probably will find a bit odd, but I just would like to share it anyway. So far we have looked at RF only from the perspective of waves and powers, but you can also look at voltages. Yeah? So when you, for example, here, this first of all, this is a comparison model versus the measurement. Yeah? So this is why there's two types of sets of curve, one in blue, one in red. And we check our models in this way whether they really describe the transistor well. And what do you see here? You see, for example, the current of this transistor dynamically over the voltage. So this is the essentially the representation in reality of this. Yeah, so this is really checking the current at 10 gigahertz calculated from measurements. And you see the dynamic swing here. So this is really the dynamic change. You see this is not going down to zero. There's a knee. And you see it's also not, there's a zero here. The zero line is here. And it's reaching here a maximum of, so this is biased here at 25 volts. And you see it's going up to 50. So it's really symmetric around the 25 volts. So that makes a lot of sense. Yeah. So like, sine wave just goes in there. Here you see actually the sine wave, yeah. So, and you see it starts with a sine wave. But I haven't explained why are there different curves. So why are there multiple red curves? Why is this a bar and not just a single line? That's very simple because we plotted for each of these curves here. So for each point. And the higher the power, the higher the swing also. Yeah? So the power is going up, and you see that the voltage is actually maximized here. Yeah? And you see that also here, this is the input characteristics, which is just a normal straight line. It goes along this. And then when you start to put more power in it, it starts to also to run up. Yeah, that's one thing. And you see then, this is then why we are doing this. You see also for low power values, you see a perfect sine wave. But when you're starting to compress, this sine wave also is modified. So you see compression not only from coming down in power, so so what we call saturation here. So the power is not going up linearly anymore with the input power. And you see that here that also so this is the low input power thing. This is a perfect sine wave, yeah. And you see then for high power, it starts really to create some uneven shapes, which is just a representation of compression. And the other thing why I'm putting this up is, in this representation, if we just draw the current, we don't see any RF, because then it's lost, because the information, this is very principally what we see here. And the capacitances you see here in this blowing up of the curve. So this is, for example, the simple characteristic of the output current over the input voltage. This is this here, so this, but it's blowing up. And why I like this is something you know, because we know there are capacitances in this FET. And if you think that from a power perspective, is what do you get? You get real power and imaginary power. So what it means is that we are driving some of the power also in arbitrary power, imaginary power. And that's why then the curves, they are going along the normal path, but they're also blowing up. So we are pumping power into this device, but it's not getting out. It just stays there. So this is really a representation of what you may know from power electronics, from networks. We are pumping power into this, and the imaginary part especially shows them. That's why these curves, in some reasons, there you see for the currents especially, and also for the input characteristic. That's why it starts to really blow. And you can measure that. If you take the right equipment, there's a chance really to see the RF current, which is what you're looking for. Adding a bit to the field effect, there's a couple of things which I'd like to add, just to we now need a little bit of relative understanding why the MOSFET is good and some other things are not so good. So, for example, one thing which is very important there is that we could also make a FET without that MOS. We could also take a junction, so we could take a PN junction in here. Why don't we like that? Just based on what I just showed you with the RF control. What is your answer there? What is the principal advantage of a MOSFET? Why is that good to have this MOS diode there instead of some junction diode? It's actually quite simple. What in other contexts, when you have two types of carriers, why is that sometimes problematic? For example, if you have heard power electronics already, which devices are faster, unipolar or bipolar? It's good. So I think you mentioned the Schottky diode already. Why do we like Schottky diodes so much? I think you mentioned it earlier already. What is your feeling? It's important because this is something which helps to sort these ideas, because the MOSFET is very nice because we are driving this only dynamically. So we are not sending any current here into this oxide. It's just a dynamic change. It's just the field we modify. While in the junction FET, we are providing also current through DC current to bias it. And then you have all these P and N carriers near the interface, and you have to charge them. And that's something maybe that helps you also in the understanding. When we have a MOS cap, we only have the cap based on the field effect, so to say. While if you have a PN junction in there, there's also the junction capacitance, which adds. So this thing it's very simple. The junction things are very slow. You can do megahertz with them, but never really gigahertz. Yeah? So that's why the MOSFET made such a career, because by definition, because you have this sharp current control and not driving currents into the gate where the structure is sensitive to speed changes. That's why the MOSFET is so particularly attractive. There's also something which in a MOSFET we talked a little bit about the carriers and the threshold, and there's two things now. First of all, there's N conduction, which we just talked about. So we had the electrons flowing in the P substrate, but you can also, as you know, in the complementary MOS, we can also make P transistors, which is a P channel in an N environment. And this is helpful because when you have when you do it right, you get this combination, which just gives us a complementary logic because both voltages and current are both inverted. That's great. Then you can do this complementary idea. But there's also other types. So, for example, the normal MOSFET we are using for N-type, so the one which we just talked about, typically has a positive threshold voltage. So you bias it at plus something and you get voltage and current. But it's not always the case. Many RF devices also have a negative threshold, although the current is positive. So that's something which is, and we call one type is an enhancement type, so we have to do something to turn it on. And if it's a depletion type, we have to do something to turn it off, which is a bit stupid, because then you have to invest energy to turn something off, and that is a bit of a contradiction. So it's better if something is off, if nothing happens. So this enhancement type is a very nice feature, which often you can make, but not always. So a lot of very good and fast RF FETs are also of this type. It depends a bit what type of device it makes. Yeah. And the other thing where silicon is very advantageous, but I think I mentioned it, in silicon we have N conduction and P conduction, and they are similar. In most of the other semiconductors we don't have that. So, and generally the electron-based mobilities are better. In most of the devices, the N-type is actually the better RF structure. Yeah. Okay, I'd like to stop here. What I would like to do next time is to get a relatively comparison. So I was now heavily bashing the bipolar idea in terms of speed, but that's a bit unfair because the FET is a very good combination because we have this high forward current and we can easily reduce the capacitances when we do this nice lithography. And in a bipolar, I already mentioned that we might introduce the capacitances. That's true. Yeah? But at the same time, the bipolar also has an enormous current driving potential. Yeah? So you can really push things really to the limits. The fastest devices in some aspect are really also bipolar if you do it right. So it's just, we're getting essentially similar frequencies with both types. And what I would like to explain next time is that the bipolar is particularly advantageous because it can realize current amplification on a small area. Now you could say, why am I interested in that? Or you? But the reason is that what I said, the difference is about the difference of a tablet and the cell phone. Yeah? If you would build a cell phone with FETs, it would have the size of a tablet. That's why we use bipolars, because you want to be able to put your cell phone in your pocket. Yeah? So this idea, which you have here, that you have this combination of how much forward current can we create, that's an absolute number. Yeah? So that's interesting. But in a bipolar, we can also put the same GM on a very small scale. That is extremely attractive because then you can build something small. And that by far gives you a potential to make things smaller, not necessarily faster, but you have a lot of current drive, and that's why things are good. So this concept which we just looked at for the FET is distinguishably better for the bipolar and has some clear advantages also. So that's something for the review. Okay, other questions or concerns? Anything you would like to see again? I did cover a lot of ground today, actually. Anything you would like to be asking for? I will introduce also, because we spared some time, I'll introduce a little bit more on the modern MOSFET. So what do you really have in your pocket? Because as I mentioned, they don't look like this anymore. They have the same principles. You need to know all that, but they're just really 3D devices by now. So this is really, so the 3 nanometer stuff is really crazy because you have to think these concepts in 3D now, but it's useful. So you will enjoy it when playing some fast game on your cell phone or whatever. You just get the benefit of what we just discussed. Okay, then thank you very much.